In this topic, the conditions for current flow in a circuit will be described. In addition, hazards associated with opening and closing circuits will be discussed, along with techniques for mitigating the risks. Power consumption in parallel circuits will be introduced. Let's now look at the case where we have a lighting circuit shown here, which is waiting to be energized by the 100-volt battery. So first off, we connect the positive terminal of the battery to the positive terminal of the circuit. Under these conditions, how much current will flow through the circuit? Well, the answer, of course, is 0. Look, we still need to connect the two negative terminals together. This brings us to a very important observation. That is, current will not flow and no work will be performed until the circuit is completed. A complete path must be provided to and from the voltage source and to and from the circuit elements. One point that we should be aware of is that as we try to make the final connection to complete this circuit, there may be a considerable amount of sparking as the current tries to flow and energize the lighting circuit before we have completed the connection. We are aware, of course, of a similar situation that occurs when we disconnect the circuit when the lighting is no longer required. Now, while this sparking may be considered to be insignificant at these low voltage, low amperage circuits, there may still be a fire hazard or explosion hazard due to gases venting from the nearby battery. However, the problem becomes really serious when we are interrupting circuits carrying several thousand amps. For this reason, on high voltage circuits, special switching devices must be installed, such as circuit breakers, interrupters, and so on. For our small lighting circuit, it will be sufficient to install a manual switch in the main circuit, and this will be opened while connecting the battery to the circuit. Now that we have become familiar with this circuit, let's take the opportunity to practice more Ohm's Law calculations, this time with two resistances in parallel. In each branch, the flow of current equals 100 volts divided by 100 ohms equals 1 amp. The total current supplied to the two circuits is, of course, 2 amps. The power consumed by each branch circuit is equal to I times V, that is 1 amp times 100 volts equals 100 watts. What will be the energy consumed in watt-hours during half an hour? Energy equals watts times hours equals 100 watts times 0.5 hours equals 50 watt-hours. For each branch, how much power is supplied by the battery? Here we have a current of 2 amps times the voltage of 100 volts equals 200 watts. Looking at the same circuit, suppose we added another resistor in parallel, but this time its value is 50 ohms. Now, the current in this third circuit will equal 2 amps, and the total current being supplied by the battery is now 4 amps. With parallel circuits, we can simply calculate the current in each branch and add these in order to arrive at the total current required.